Okay, so welcome to this next video in the playlist on group theory. In this video, what we're going to discuss is the concept of a group action. Okay, so the way we're going to approach this is we're going to start off by discussing the motivation for a group action, what we're actually trying to achieve. Then what we'll do is we'll go through the formal definition of what a group action actually is. Now the formal definition of a group action looks quite far removed from the actual motivation of what we were trying to achieve. So we'll then spend a lot of time trying to understand why this formal definition of a group action actually achieves what we set out to achieve, basically. Okay, so we'll spend a lot of time trying to understand the formal definition of a group action. Okay, but I want to stress this is a really important concept and we're going to use it in a lot of what we go on to do later on. Okay, right. Firstly then, let me give you the motivation for a group action. Okay, so throughout this playlist on group theory, we have seen that it is often helpful to think of the elements of a group as representing set permutations of some set. Okay, and then think of the composition law on the elements of the group, the composition of the symbols within the group, as representing the composition of the set permutations that those symbols represent. Okay, basically, group actions is a way of formalizing this concept, formalizing the concept that you can associate with elements of a group set permutations of some other set. Okay, because one of the questions that you might have been wondering throughout the playlist on group theory is it the case that we can only ever associate set permutations of a single set with the elements of a group? Okay, so for each group, is it the case that there is only one set for which you can associate the set permutations of that set with the elements of the group? And the answer is of course not. If you've got a group, you can associate the elements of that group with set permutations of a huge number of different sets. Okay, so group actions is going to put this concept of associating set permutations of some set with the elements of a group on firm ground, basically. It's going to formalize it. Okay, so that's what we're trying to achieve. We're trying to formalize this concept that we can associate elements of a group with set permutations of some set. Okay, so let's now go on to the formal definition then of what a group action actually is. Okay, so firstly let's just do the setup. So what we need is some group. Okay, so we'll have some arbitrary group, capital G here, and I'll underline our group in turquoise here. And of course we know by now what a group actually is. This will be a set of symbols, so I'll draw the set of symbols here. So here is our set of symbols, and of course it has a composition law defined on it, so I'll put its composition table here. Okay, so this is our group, a set of symbols with a composition table here defining composition of any two elements of that set. Okay, so in order to define a group action we need some group, so here is our arbitrary group. The other thing we need is some set for which we are going to associate set permutations of that set with the elements of the group. Okay, and it's common notation to call the set capital A. Okay, so we'll have our set here, and this now is just a set of symbols. Okay, and it can be, again, an arbitrary set of symbols, but this is just a set. It doesn't need to have a group composition law on it. Okay, so these are the two things that we're going to need to be able to define a group action. We need a group, and we need a set of symbols, and we're going to associate the elements of the group with set permutations of this set of symbols, capital A here. Okay, right, so now a group action by the group capital G on the set A, the strict definition of this is that it is a function. Okay, so we'll call the group action little f here. It's a function from the Cartesian product of the set that underlies the group capital G with the set capital A to the set capital A, basically. So this is the strict definition of a group action, that it is a function. Okay, so this thing here, this function, is the group action. Okay, strictly speaking, what we'd call it in full is the group action by the group G. Okay, so I'll get rid of that S there. Group action by the group G on the set A. Okay, so that's in full what we'd call this. We'd call this a group action by the group G on the set A, because what we're going to see later is that really the elements of the group are acting on the set A. Okay, they're going to be associated with set permutations which act on the set A. Okay, right. So, going back to this definition then, okay, let's firstly discuss what the Cartesian product here of the set that underlies the group capital G with the set capital A actually is. Okay, and I want to stress that although this is the same nomenclature that we used for product groups in the previous video in this playlist on group theory, here, this cross here represents the Cartesian product of these two sets. Obviously this is not a group, so this cannot be a group product between these two. Instead, this is just a set product between the set that underlies the group capital G here and the set that underlies, well, the set capital A in this case. Okay, so let me firstly just draw out a picture of what the Cartesian product of G with A, this G cross A, actually means. Okay, so firstly actually I'll just write out what it means. Okay, so G cross A is the set of all things of the form GA, where little g is an element of the group capital G, and little a is an element of the set capital A. Okay, so the Cartesian product of the set that underlies the group capital G with the set capital A means put into a set all the ordered pairs of elements from the set that underlies the group capital G and the set capital A. And that's what we mean by the Cartesian product. Okay, so I'll just underline this in vivid purple here. So it's all things of this form, little g, little a. So you can let little g go over every element of the group, and for every element of the group that you put in this first socket, you let little a vary over all elements of the set capital A. Okay, so you get every possible combination of an element from the group with an element from this set capital A. Okay, now we can draw a nice picture of what this actually means. Okay, so we can draw a table. So I'll draw this now. Okay, so the way that you can visualize what the Cartesian product of two sets actually means is you can imagine drawing a table like so, and what you can do is you can put all of the elements of the group capital G here down here, so you can give every single element of the group a row in this table. Okay, so for all the elements of the group you're going to give them a row in this great big table, and then for all of the elements of the set capital A you can give them all a column. So you'll go through every single element of the set A and you'll give them all a column. Okay, so let me colour this in. So here we'll have our set capital A coloured in red here. Okay, and we've coloured our group in turquoise, so we'll stick to that. So we'll have all of the elements of our group down here given a row, and we'll colour that in turquoise. Okay, and then what you can do is you can go in and fill out all the entries of this table, and the entries of this table are going to be the ordered pairs. Okay, so what you'll do is for each element of the group, you will go along all of the different columns corresponding to all of the elements of the set A, and you will pair that element of the group with every single element of the set A. So to give you an example here, let's take the row here that corresponds to an element little g, okay, and let's take the column here that corresponds to the element little a of the set. Then the entry in this table here, and I'm not going to try and squeeze it in there, but the entry that would be in this little square here would be the ordered pair little g, little a. Okay, so this is a pictorial representation of what the Cartesian product set of G with A actually means. You go through every element of the group, and for all of those elements of the group, you pair them with every single element of the set capital A. Okay, so visualizing this in terms of this table here is actually going to be very, very helpful, so we'll come back to this in a moment. Okay, so that's what is meant by this Cartesian product then of G with A. Okay, but let's go back to what the group action actually meant, because the group action was more than that. The group action was a function which maps every element of this ordered pair, every element of this Cartesian product set of G with A, so every ordered pair in this Cartesian product of G with A, onto an element of the set A. Okay, so to give you a bit more notation, the group action F is going to map all ordered pairs. Okay, so we'll take an arbitrary ordered pair from our Cartesian product of G with A, and this will look something like this, GA, okay, and it's going to map it onto an element in this set A, and we have a piece of notation which we're going to be using all over the place in this video, so I might as well introduce you to this now, okay, for the element that this ordered pair will be mapped onto, and it will be mapped onto an element that we're going to call G dot A, and you put the dot sort of at the bottom here, so it's in between the two elements, but it's not sort of in the middle there, so it's not like G dot A like that, you put it sort of towards the bottom, so more like there, okay, so between the two, but at the bottom of them, okay, and the way that you would read this is the element little g acting on the element little a, okay, and the answer to this is some element in the set capital A. So this G dot A means what the group action F will send the ordered pair GA onto, and it's an element in the set capital A, basically. Okay, so that's a bit more notation regarding group actions being these functions which are mapping the Cartesian product set of G with A onto the set A. Okay, right, so to take this further, and I should just say, this definition isn't complete yet. This mapping needs to obey a bunch of axioms that I haven't even begun yet. Okay, but at the moment I'm just discussing what this mapping actually means. Okay, so what this is really doing is it will take every element of this great big table that I've drawn out here, and it is going to be mapping it onto some element in the set A. Okay, now, the nice way of visualizing this is to visualize it again as a table like this, okay, but instead of actually putting all of the ordered pairs in the table this time, what we're going to do is replace the ordered pairs with what this function f maps the ordered pair onto, okay, because although we didn't actually discuss this at the time when we were defining what a group was, this is actually the formal way of writing out what a composition table is. Okay, so let me just discuss this in a little bit more detail so that I can motivate my next move. Okay, when we went through the definition of a group, okay, we saw how a group is a set of symbols with a composition law defined on it. Okay, so you can compose any element of the group with any other element of the group. Now, when I defined a group, I just sort of, we just ran with it. We just saw a composition table like this intuitive picture of what a composition table is. But the actual formal definition, the formal way that you define what a composition table is that it is a mapping from the Cartesian product of the two sets that you want to compose elements within to whatever set you want the answers to be in. Okay, so the formal way that you would define a composition table on a group is you define it as a function from the Cartesian product of the group with itself to the group. Okay, and I want you to understand why that is. So if we took the Cartesian product of G with itself, what we'd really be thinking about is, again, a table like this. So we'd put all of the elements of the group down here, we'd give all of the elements of the group a row in our table here, and we'd give all of the elements of the group a column of the table up here, okay? And then what we'd go through and do is we'd go through and work out what all of the ordered pairs here are, and then this function f will be mapping all of these ordered pairs onto other elements within the group capital G. So what you can view the composition table as is this table here, where we've got all of the ordered pairs of an element from the group with another element from the group, but instead of actually putting in the ordered pairs here, instead what we put in is what this function f would map that ordered pair onto. Okay, and that would be some element of the group back again. So what we do, instead of putting in the ordered pairs in this table now, instead what we do is we put in the elements of the group, and that's exactly what a composition table is. Okay, so what you can then do is go through any combination of two elements from the group, and then you'll get the answer to what those two elements composed together is equal to, and it'll be some element of the group. Okay, so that is the formal way that people define what a composition table on a group actually is, that it's a function from the Cartesian product of the group with itself. Okay, and you can think of that just as a table of ordered pairs, and then it's mapping all of the ordered pairs onto an element of the group itself, and then you can just imagine replacing the ordered pairs here in this table with what this function would map that ordered pair onto, and then you've got your composition table. So that's the formal way that people go about defining what a composition table on a group is actually equal to. As I say, we didn't actually do that when we were introducing the concept of a group, because it isn't actually really that helpful to know this absolutely formal definition. Just having an intuitive view of what a composition table is all you actually need when you're actually doing group theory. Okay, right. Similarly, what we can now do is view this function, which is this group action, as being a composition table, but this time, rather than being a composition table of elements of the group with elements of the group, it's a composition table of elements of the group with elements of the set A, and the answers, rather than being back within the group, they are in the set A. Okay, so what we can now do is we can take this table of ordered pairs of elements of the group and elements of the set A, and we can replace all of the ordered pairs in this table with what they've been mapped onto by this function, basically, which is an element in the set A. So what I now want to do is build a group action composition table, and this is how I would urge you to intuitively view what a group action is, as a composition table between elements of the group and elements of the set A, where the answers to the composition are elements of the set A back again. So we're going to take this table and we're going to reinvent it slightly. Okay, so here is this table moved down here. So what we're still going to have here is all of the elements of the group are going to be given a row. Okay, so every single element of the group will have a row dedicated to it. And once again, I'll colour the group elements in turquoise here. And then all of the elements of the set A on which the group is going to act are going to be given a column up here. So once again, we'll have all of the elements of the set A up here with a column dedicated to them. Okay, so I'll colour this portion once again in red, which we're using to denote our set A. Okay, and now instead of having all of the ordered pairs as the answers within this table, instead what you're going to do is you're just going to put the answer to what all of the ordered pairs will be sent onto by this function f, which is our group action, basically. Okay, so once again, to do an example, so let's say we have the row dedicated to this element little g here. Okay, so this is the row in the composition table dedicated to the element of the group little g, and let's say we have this column in the composition table which is dedicated to some element of our set capital A, and this arbitrary element of the set capital A we'll call little a. Now the entry in the composition table, rather than being the ordered pair GA, is going to be the answer to what that ordered pair is sent onto by the function, which is g dot a. Okay, so really this is what you should view a group action as being. A great big composition table like so, where we are composing the elements of the group capital G with the elements of the set capital A. We're calling this composition dot, or acting upon. Okay, and all of the answers in this composition table are elements of the set capital A. Okay, so that's the intuitive way of viewing what a group action is. We are defining this composition table of the group with the set A, and the answers are in the set A. Okay, however, you cannot just make up this composition table arbitrarily and call it a group action. This composition table has to obey a bunch of lovely properties to actually make it interesting and worth studying. If you just make up the answers here and stick in whatever elements of A you like in all of the slots in this composition table, you will not end up with a group action. You will not end up with something that is worth studying. Okay, so in order to be a group action, in order to be something interesting that is worth studying, it has to obey a bunch of axioms, a bunch of properties. Okay, and there are only two properties that it needs to obey, and we're now going to go over these. Okay, so the properties then that this composition table needs to obey. So property number one is really, really important. In fact, both of these properties are really, really important. Okay, so property number one then. Property number one says that if you pick any two elements from the group capital G, okay, so for all, that's the mathematical symbol for all little g1 and little g2 that you pick from the group. So pick any two elements that you like from the group. I'm just going to call these arbitrarily little g1 and little g2. It needs to be the case, okay, it must be the case that g1 dot g2 dot A must be equal to g1 composed with g2, where this is composition in the group, and then that answer dot A. Okay, so we'll spend a little bit of time going over exactly what this means. Oh, and I've missed a line out of this. Okay, so I should have put for all little g1 and little g2 is an element of the group, and for all little a is an element of the set capital A. Okay, so this relationship has to be true not only for any little g1 and little g2 that you take from the group, but also for any little a that you pick from the set. Okay, so this statement must be true. Okay, so let's just think through what these two sides of this equation actually mean. Okay, let's appreciate how the two sides of this equation are actually different. Okay, so firstly let's take the left-hand side. So all of the compositions here are in the group action composition table. So firstly, let me just draw out the group action composition table here again. Okay, so once again what we'll have is all of the elements of the group here given a row in this composition table, and once again I'll colour it in. So here are all of the elements of the group in turquoise, and then we'll have all of the elements of the set capital A given a column in this composition table, and once again I'll colour in the set A in red here. Okay, so what we've now done is picked two elements from our group which we've called little g1 and little g2. So let's just mark those on here. So we'll have little g1 here, so this is the row in the composition table that corresponds to this element little g1. Okay, then we'll have this element little g2, and we'll say that this is the row in the composition table that corresponds to this element little g2. So I'll just colour code those up. So here is little g1, so we'll have that coloured in blue here. Then we'll have little g2, and we'll have little g2 coloured in pink here. Okay, then what we need is the element little a. Now the element little a is from the set, so we'll have a column dedicated to this element little a here. Okay, let's say the column dedicated to the element little a is here. Okay, right, so what are we doing then on the left hand side here? So we take little g2 here and we act little g2 on the element little a, and the answer that we will get will be this answer here, this entry in our group action composition table. Okay, so the entry here is g2.a. So this portion we've just worked out of the left hand side is this entry in our group action composition table here. Now, whatever that answer is, what we do know about it is that it is another element of the set A. Whatever G2.A is, it has to be another entry in the set A, because all of the elements that we put in this group action composition table, they are all elements of the set A. So what we can now do is take this element of the set A and we can act G1 on it. Okay, so G2.A will be some other element of the set A. Okay, so it will also have a column dedicated to it, so I'm just extending my composition table here. Okay, so here is its column that's dedicated to it. And now what we're going to do is we're going to ask what is G1 dot this answer G2.A, and of course the answer to that is this entry here. So this entry here is G1 dot G2.A. So the brackets tell you what to do first, as they usually do in maths. Okay, so here is our element G2.A highlighted in green there, and then the entire answer to the left hand side is then this entry in the composition table here. So the left hand side of this equation is equal to this entry here. Okay, so that's what this side of the equation means. That's what it's commanding you to do. What does the right hand side of this equation actually mean? Okay, well, in this case, what we're going to do is we're going to use the group composition table first to compose together G1 and G2. We're then going to take the answer to that and we're going to act that on the element A within the group action composition table. So I'll add on to this picture the group composition table here. So what we're going to need is we're going to need G1 in the group composition table here, and we're going to need the element G2 in the group composition table here, and what we're then looking up is what is the answer to G1 composed with G2. So we look at the row dedicated to the element G1, we look at the column dedicated to the element G2, and we get this answer, what is G1 composed with G2, okay, and we get some answer that is again within the group. Okay, then what we're going to need is we're going to need the row dedicated to this element G1, G2 in the group action composition table. Now where shall I put this on in this picture? I might try and squeeze it in here. Okay, so let's say that this row here is the row dedicated to this element G1, G2, just for lack of space. Okay, so what colour have I coloured G1, G2 in turquoise here. So here is G1, G2, and this entire row here in this group action composition table we are saying is the row dedicated to this element of the group G1 composed with G2. And then what we're going to do is we're going to take G1 composed with G2 and we're going to act whatever that answer is on the element A. So this time the answer on this right hand side is this answer here in the group action composition table. Okay, so this is the answer on the right hand side. So that is what these two different things actually mean. So you can see blatantly that they have different entries in this group action composition table that actually correspond to their answers basically. So they do mean different things. If this group action composition table is indeed going to be a group action, then it must be the case that no matter which little G1 and little G2 and little A you pick, this relationship always holds true. That it does not matter if you firstly compose G1 and G2 together in the group composition table and then act that answer on the element little a, or if you firstly act G2 on the answer, on the element little a, and then act the answer to G2.a, you act G1 on that answer basically. It does not matter which way round you do it, the answer must be the same. Okay, and that is a big ask. If you were just to make up this group action composition table and stick in arbitrary elements of the set capital A into this composition table, you would almost certainly not get this to work basically, unless you actually knew what you were doing. Okay, right, so that is axiom number 1 then of group actions. That is one of the big properties that a group action must obey. But there is a second one as well, and I'll go on to the other side to introduce you to the second axiom of group actions. Okay, so the second property then that a group action must obey is slightly easier to understand. Okay, and this relates to the identity element of the group. So basically what axiom number 2 says is that if we represent the identity of our group as E here, E must act on any element of the set A, so E dot A must equal the element A again. Okay, so the identity must act on any element of the set to give back that element of the set. Okay, so E dot A must equal little a for all little a is an element of our set capital A. Okay, and again this has a nice picture understanding that we can get. Okay, so once again I'll draw out my group action composition table here. Okay, so this is my group action composition table, and of course I'll have the entire set capital A up here. They will all have columns dedicated to them, and once again I'll colour this in red here, and then we'll have all of the elements of the group given a row down here. Now the particular element of the group that we are now interested in is the identity element, so we might as well put the identity element right at the top up here. Okay, and let's say this then is the row dedicated to the identity element in my group action composition table. Okay, so what we're now going to do then is we're going to go through and we're going to act the identity element on every single element of the set, and we need to fill in this entire row of entries. And basically what this property number 2 of group action says is that if this composition table is going to be a group action by the group G on the set A, then the identity must take all of the elements of the set, act on them, and return that same element of the set back again. So basically what it means is that this row of entries here of the set A is an exact replica of the row that we've got up here basically. So we've got all of the elements of the set up here given a column, and they're in a certain order, and basically just take that row, copy it, and stick it in here. So stick all of the elements of the set underneath themselves here, and that's what this row corresponding to the identity element of the group is actually going to look like if we're dealing with a group action here. Okay, and that's property number 2 of group actions, that the identity element must act on any element of the set to return that element of the set back again. Okay, and those are the only 2 properties then that a group action actually needs to obey. Okay, right, so I warned you right at the start that the definition of a group action would seem kind of removed from our initial motivation of trying to formalize this association of set permutations of a set with elements of a group. Okay, and indeed at the moment it may well seem like that. In the next video what we will do is we'll have a look at how defining one of these group actions, one of these group action composition tables that we've gone through now, actually allows you to associate all of the elements of the group, capital G, with set permutations of the set, capital A.